Hello guys, hope you are doing well. In today's video, we will be talking about the chapter 2, section 2, which is about the two other definitions of the acids and bases, which are the Bronsted-Lowry and Lewis, and we'll be talking about the types of the acids in terms of containing protons, the monoprotic, diprotic, and polyprotics, triprotics, which are the polyprotics. Guys, the second definition of the acids and bases in our curriculum, it's all about the Bronsted-Lowry, and let us talk about the Bronsted-Lowry acid, and then we'll be talking about the Bronsted-Lowry base as well. Refer back to the Arrhenius definition. The Arrhenius, it was about the increase in hydronium and hydroxide concentration for the acids and bases in their aqueous solution. But the Bronsted-Lowry provided another conditions to classify the compounds, molecules, ions as the Bronsted-Lowry acid or base, which is the donation or acceptance of proton. So guys, the Bronsted-Lowry, according to Bronsted-Lowry, the acids are what? Acids are those compounds which they are those compounds which the acids are those compounds, molecules, ions that they donate a proton. Any molecule or ion that has proton and has tendency to donate that proton, it can be classified as what? As the Bronsted-Lowry acid. The H positive, guys, we call as a proton. Why? Because whenever the hydrogen, which has an electron with a proton, lost the electron, it will be H positive. And then it will be without electrons, and then we will call as a proton because it consists of a proton only. All acids, as defined by Arrhenius, donate protons to water and are Bronsted-Lowry acids as well. Guys, we can say that all the Bronsted-Lowry acids, they are we can say that all the Arrhenius acids, which they increase hydronium, they have to donate proton to the aqueous solution to increase hydronium, so they will be classified as Bronsted-Lowry acids. But the reverse process is not true, because we have some Bronsted-Lowry acids, they are donating protons, but they do not be classified as what? As the Arrhenius acids. Like, for example, here we have an ion. The HSO4 negative is going to donate a proton to water and then increase the hydronium and left the sulfate behind. Here, guys, the HSO4 negative is only a Bronsted-Lowry acid. It cannot be defined as Arrhenius acid. Why? Because it's ion. If you remember, we said the Arrhenius should be the neutrals, not the ions, and in aqueous medium as well. So Bronsted-Lowry has no restriction for the medium. We'll be talking about that later on. And have a look on this example, guys. Here HCl is donating a proton or transferring a proton to ammonia. So the HCl is a proton donor and becomes an Arrhenius acid, a Bronsted-Lowry acid. Also, here we have got the ammonia, and the ammonia is a proton acceptor, so it becomes a Bronsted-Lowry base. Guys, the Bronsted-Lowry definition has restriction of medium substances which donate or accept proton, has no restriction of medium, are classified as Bronsted-Lowry regardless to the medium of reaction. Example for that, guys, we have got here an example, the figure which is provided. Here, this figure 9, from hydrochloric acid, the hydrogen chloride gas escapes, and from the ammonium, which the ammonia solution, it goes to form ammonia gaseous, and then in the cloud of these two, they mix and react to form ammonium chloride, and this is a salt suspended in the air. And guys, this HCl in this case is in the gaseous medium. Ammonia is in the gaseous medium, but we call as HCl as the Bronsted-Lowry acid, and ammonia as Bronsted-Lowry base. Why? Because the HCl donates a proton and ammonia accepts that proton regardless to the medium. The Bronsted-Lowry the ions and molecules can be Bronsted-Lowry acids and bases regardless to the restriction of the medium, and also the ions can be as Bronsted-Lowry acids and bases as well. We said Bronsted-Lowry acid is a proton donor, and then a proton donated by a molecular ion must be accepted by another molecular ion. So a Bronsted-Lowry base is what? Is a molecular ion that's a proton acceptor. The one that donates must be accepted by another one, which we call as the Bronsted-Lowry basis. Guys, for the Bronsted-Lowry, we have some restrictions in the bases. Only the molecular bases can be Bronsted-Lowry bases. The ionic cannot be Bronsted-Lowry bases. Why? Because there will not be transferring of proton for the ionic bases, which we mean the metal hydroxides. Guys, the arrhenius hydroxide bases such as sodium hydroxide, the metal hydroxides, are not strictly speaking Bronsted-Lowry base. So we mean the metal hydroxides cannot be classified as Bronsted-Lowry bases. Why? Because there will not be any transferring of proton. Have a look, for example, NaOH, guys. When it dissociates in water, it will produce Na positive plus hydroxide. We cannot see any transferring, donation, or acceptance of proton in this mechanism. So NaOH is not a Bronsted-Lowry base. Instead, it's just only arrhenius base. But guys, be careful about that. The metal hydroxide themselves, they are not Bronsted-Lowry base, but they will produce an ion which can be a Bronsted-Lowry base in other reactions. For example, when hydroxide reacts with the hydronium to form H2O, okay guys, 2H2O, here in this case, the hydronium is going to donate a proton to the hydroxide. This becomes a Bronsted-Lowry acid, and the hydroxide is a Bronsted-Lowry base. So the notice that you have to know that the metal hydroxide themselves, they cannot be classified, they are not defined by Bronsted-Lowry definition, but they will produce an ion which defined by the Bronsted-Lowry, and it becomes a Bronsted-Lowry base. So guys, Bronsted-Lowry is used only for molecular compound. As I told you, we have only molecular bases that can be classified as Bronsted-Lowry. Water can also act as Bronsted-Lowry acid. We define it according to the Arrhenius. Water was just a solvent, a medium. It was neither acid nor bases. But according to Bronsted-Lowry said H2O is amphoteric. We will be talking about amphoteric in the coming section. Amphoteric means what? Means it can be acid and base as well, but in two different reactions, not in the same reaction. So in the same reaction, it can be classified as base only or acid only, but in general, in two different reactions, two different mediums, it can be in one medium acid, in the other medium as a base. For example, guys, have a look here. Here H2O donates a proton to ammonia, so it's a proton donor and it becomes a Bronsted-Lowry acid. It becomes a Bronsted-Lowry acid. Let me provide an example that water becomes a Bronsted-Lowry base. For example, HNO3 plus H2O will produce hydronium and nitrate ion. So in this case, H2O is going to accept the proton, so it becomes a Bronsted-Lowry base. So the Bronsted-Lowry acid in this example and the Bronsted-Lowry base. So water, according to Bronsted-Lowry, is amphoteric, which can be both acids and bases in different reactions. We have no reaction for the arrhenius, but we have reaction for the Bronsted-Lowry, guys. Bronsted-Lowry reaction represents a reaction which protons are transferred from one reactant, the acid, to the other one, which is the base. So always in Bronsted-Lowry reaction, there must be two acids and two bases, guys. Two acids and two bases. An acid plus a base will produce a cation usually plus an ion. This is usual case, that guys, we have exceptional. So the acid and the base and the cation becomes we'll be talking about the conjugate. It will be a conjugate acid and the anion usually a conjugate base. So the acid and the conjugate acid are both acids. The base and the conjugate base are both, they deal with as the bases. So any reaction is in this form classified as a reaction of Bronsted-Lowry reaction, because such type of questions appears in ministerial exam several times. Here we have a note, guys. If the Bronsted-Lowry reaction, there are two acids and two bases, one in the reactant and the other in the product. So Bronsted-Lowry reaction, always there must be two reactants and two products. There may be questions asking which this equation is defined, or the reaction of which of the following definitions, defined by which of the following scientists. You have to know that the Bronsted-Lowry, there should be two reactant and two product always in order for a reaction to be a Bronsted-Lowry reaction. And we talked about this. This is about the medium. The Bronsted-Lowry has no restriction of the medium, and it said when a hydrogen chloride gas combined with ammonia gas in air, which of the following mixture will form? Of course, colloids will form. Why? Because the suspended ammonium chloride solid suspended in the medium in the air, and then it will be a colloid. As you know that a suspension or a suspended particles in a medium, it will be a colloids. Guys, one more note for the, we have some other bases like caffeine. Many medications contain bases, and a beta test is a property of bases, so many medications are bases. You'll see that they often contain nitrogen. Most of the bases, the weak bases, usually the molecular bases that contain nitrogen, like caffeine, guys, which acts as a stimulant on the central nervous and respiratory system. Its molecule is given here. It's C8H10N4O2. Like ammonia, caffeine has basic property because it has a nitrogen. So any compound like caffeine, amines, the codeine, aniline, they contain nitrogen. They can be classified as Bronsted-Lowry bases. Which of the following compound acts as a weak Bronsted-Lowry base in aqueous solution? Of course, C is the correct answer, which is the caffeine, C8H10N4O2. Here we have got several examples. I will be solving a few of them in terms of species, in terms of reaction as well. The first one, guys, HCl produces hydronium and chloride by donating a proton, so it's Bronsted-Lowry acid, and HCl increases the hydronium, it's the arrhenius acid as well, but H2O only Bronsted-Lowry acid. And the reaction is a reaction of Bronsted-Lowry reaction. Why? Because we have got two reactants and two products, and Arrhenius has no reaction. The same here, guys. HNO3 donates a proton, so it's Bronsted-Lowry acid, and Arrhenius acid as well, because it increases the hydronium. H2O is what is Bronsted-Lowry base. Sorry, here you have to say base. Bronsted-Lowry base. Why? Because accepts proton. The same for, but have a look on NaOH, guys. NaOH, that just increases the hydroxide. That's why it's a Arrhenius base, but it's not Bronsted-Lowry base, and the reaction is not Bronsted-Lowry reaction as well. This is a physical change only. The same for barium hydroxide. Barium hydroxide just increases the hydroxide concentration. That's why it's a Arrhenius base. It's not a Bronsted-Lowry base. More examples. Let me solve different examples. HSO4 negative, it donates a proton to Cn negative. So the HSO4 negative acts as a Bronsted-Lowry acid and Cn as Bronsted-Lowry base, but neither of these two are the Arrhenius. Why? Because Arrhenius are not ions. Another example for H2PO4 negative, which donates a proton to water, it becomes a Bronsted-Lowry acid, and H2O is a Bronsted-Lowry base. None of them is the Arrhenius, because this is ion and H2O is not defined by the Arrhenius as acids or bases. In terms of containing protons, guys, the acids, and they have we have got several types of acids. I will be explaining the detail here, guys. Monoprotic and polyprotics. The monoprotic refer to those acids that they contain a single proton, and the polyprotics more than one proton, which we have got diprotics and triprotics as well. Diprotics for 2 protons, triprotics for 3 protons. Guys, for every of these we have strong and weaks. Let us talk about the strong monoprotic and strong diprotic, and then we'll be talking about the weaks as well. Guys, for every of these acids, we have to answer two types of questions. First, in terms of concentration. Second, in terms of the strength of the acidity. For monoprotic strong acids like HCl, HNO3, HBr, and so on. If we take an example for them, HCl plus H2O will produce hydronium and Cl negative. In terms of concentration, guys, we do not have, the acid has no existence. So whenever the acid is strong monoprotic, and also diprotic can be stated as that, it has no existence itself. It completely ionized to form the ions. And how the ions exist, they exist equally. So the concentration of hydronium equals to the concentration of the anion. In terms of the acid strength, guys, of course, the hydronium is much stronger acid than the anion, as the ion left behind its negative charge increase that decrease the acidity. So the strength of the hydronium is a stronger acid than the anion. Maybe asked which of the following is the stronger acid in the aqueous solution of HCl. Hydronium is the stronger acid, or the strongest, and Cl negative is the stronger base or strongest base. For the polyprotics, guys, for the polyprotics only we have diprotic strongs. We do not have triprotic strongs. So for this usually we have got two examples, H2SO4, which more frequently used, and H2CrO4, sulfuric acid and chromic acid. So guys, in terms of the existence, the concentrations, let me write one of them. For example, H2SO4 equation plus H2O will produce hydronium plus HSO4 negative. The acids they have different ionization steps according to the based on the number of the protons. As much as they exist more protons, they will have more steps of ionization. 2 protons, there will be 2 steps of ionization. 3 protons, 3 steps of ionization. So in the first step donates a proton, and then this has tendency to back to reionize, further ionize to form the hydronium and then SO4, 2 negatives. Guys, as you can notice here, it becomes a double water rule, because whenever an acid ionizes, the negative left behind, it becomes weaker acid and weaker and weaker. So in terms of concentration, guys, as you can see, hydronium twice formed in the solution. It's not possible to say the hydronium has the same concentration as the anions. The hydronium produced it in 2 steps, so the concentration of hydronium must be first. Hydronium concentration has the highest concentration. And then followed by what? Followed by the anion of first step, and then anion of the second step. So we can state like that: hydronium comes first, anion of the first step, and then anion of the second step. That will be the sequence or the order of the concentration. Why anion of first step and then second step? Because here this acid is strong, produce a high amount of HSO4 negative, and then HSO4 is weak, will produce a lower amount of sulfate than the HSO4 negative. That's why the anion of the first step comes first, and then followed by the anion of the second step. The acid itself has no existence, so it has no concentration. We cannot include the acid in the concentration sequence. In terms of acid strength, the hydronium is the highest acidity, anion of first and anion of second, followed by the anion of the first. So the hydronium, anion of first, anion of second, is the sequence of both acidity and concentration. A hydronium has highest concentration and the most acidic. Sulfate has least concentration and the most alkaline. As the negative increases, the alkalinity will be more alkaline, the species. So let me ask a question and answer the question. In the sulfuric acid solution, which of the following they do have the highest concentration? Hydronium. Which of them is the strongest alkaline species? Sulfate. The least concentration? Sulfate. Which of them is the most acidic? Hydronium. So that's the possible answers and the possible questions, of course. Let us talk about, we talked about the 2 strongest, monoprotic and diprotic. Let us talk about the weaks. The weak, as the strongest, we have monoprotic, diprotic and triprotic as well. So the monoprotic weaks, like for example H2S and H2CO3. If a monoprotic is given, guys, H2S plus H2O will produce hydronium, and here we have got the that's the diprotic, guys. Sorry, we'll be doing for the diprotics, and then we'll be doing for the monoprotic as well. So hydronium and HS negative Hs negative plus H2O will produce hydronium plus S2 negatives. We'll be doing for the diprotic weak and then for the monoprotic weak. We'll be experiencing there. So guys, in this case, the concentration of the acid has the highest concentration, and then followed by hydronium, an ion of first, an ion of second. Just draw a line from the acid toward the most negative species. You'll get the sequence of the concentration. The acid, weak diprotic acid, has the highest concentration, then followed by the hydronium, then by the anion of first, anion of second. This is for the purpose of concentration. How about in terms of strength of acidity? Guys, hydronium, when we compare hydronium with the strong acid, with the acids, it's the position of hydronium is above all the weak acids and below all the strong acids. So if we compare hydronium with a strong acid, it will deal as the weakest among all the strong acids, but it will be a strongest acid among all the weak acids. That's why in terms of strength, the hydronium strength of the acidity is higher than the acid, an ion of first and an ion of second, an ion of third if it is triprotic, guys. So we have the sequence of the acidity, hydronium, and then the weak acid, and then an ion of first, an ion of second. The most acidic species in this solution is hydronium. The most alkaline is sulfide, and the highest concentration is H2S. The least concentration is S negative 2, which is sulfide. That's for for the diprotic, which is a polyprotic. Let us do for the monoprotic, guys. Monoprotics. For example, HF, HCl, and so on. Examples. Guys, HF plus H2O will produce hydronium and F negative. In terms of concentration, the concentration of the acid is higher than the hydronium, and then the hydronium equals to the anion. So here the hydronium is equals to the anion. Why? Because the hydronium and the anion form it equally in the medium, but the concentration of the HF is much higher than them. Why? Because most of the acid molecule stay as non-ionized molecule rather than the ions. So the highest concentration is HF, and then the hydronium equals the concentration of the fluoride. In terms of acid strength, of course, hydronium comes first, and then the weak acid, and then the anion. So here we have got hydronium, weak acid, and the anion, which are the strength of the sequence of the acid strength. Hydronium, the strongest acid, then followed by HF, and the strongest base or in this medium is what is F negative. That's about the monoprotic and diprotics. How about the triprotic, weak triprotics? Weak triprotic, we have got a common example like H3PO4. H3PO4 reacts with H2O to produce hydronium and H2PO4 negative. Guys, removal negative 2. It will be the next one, and then negative 3 the last. Here we have got, they are coming back to ionize further to produce this, ionize further to produce this. Okay. Removal of a proton the remainder becomes one more negative. So one hydrogen, remove it, a negative. Two hydrogen, two negative. Three hydrogen, three negatives. How to determine the order of the concentration? Because it's weak, guys, itself has the highest concentration. So from the phosphate to other phosphoric acid, the concentration increases. The least concentration is phosphate, and the highest concentration is what? Is S3PO4. That's the sequence of the concentration. S3PO4, hydronium, H2PO4 negative, SPO4 negative 2, and PO4 negative 3. In terms of the strength of the acidity, just hydronium comes first and then followed by the acid, hydronium, and then acid, an ion of first, an ion of second, and an ion of third. So the hydronium is the strongest acid, phosphate is the strongest base in this solution, highest concentration is S3PO4, least concentration is PO4 negative 3. It was a ministerial exam question, said which of the following exists in the aqueous solution of H3PO4? Of course, the answer it was all, because they were H2PO4 negative, HPO4 negative 2, S3PO4, and all of them, it will be all of them are true. So in aqueous solution of the strong acids, whether it's monoprotic or diprotic, only ions exist. But in the weaks, mono, di, tri, the acid with the ions exist. We have discussed about the sequence of the strength of the acidity and then the concentration as well. So I have provided this. Hydronium is strongest acid among all weak acids and weakest among all the strong acids if we compare the hydronium with the acids. This is explanations for the triprotics. So the hydronium, strength of the acidity, and then S3PO4, and then H2PO4, and then HPO4 negative 2, and then PO4 negative 3. That's the sequence of the acidity, and then for the concentration, just hydronium comes second, and then S3PO4 first. That's the explanation. I have explained it here, but that was the all the details I have provided for the processes. Acidity and degree of ionization decrease when with each step. So as it ionizes more, the acid, its strength reduces by each step. The last definition of the acids and bases is the Lewis's definition, guys. Lewis' definition is includes the ions, atoms, and molecules. So unlike the Bronsted-Lowry and Arrhenius, which they include, the Arrhenius includes only neutron molecules, Bronsted-Lowry ions and molecules. Lewis includes the atoms as well. So that's why this appears in ministerial exam. Which of the following definition is the broadest definition? The Lewis definition is broadest because it includes atoms, ions, and molecules. But what the definition depends on? It depends on the acceptance and donation of pair of electron. Let us talk about the Lewis acid, then we'll be talking about the Lewis basis. Is an atom, ion, or molecule. So it combines all atoms, ions, or molecule that accept an electron pair to form a covalent bond. So here we have some keywords, guys. Acceptance of electron and covalent bond as well. The covalent bond always refers to what? To the Lewis's definition. If you remember the acceptance of proton, it was in the Bronsted-Lowry for the bases. But here the acids they accept. They in Bronsted-Lowry, the acids they donate proton. but here they accept a pair of electrons. Let us see how. Guys, the bare proton, which is H positive, reacts with the ammonia. Guys, the nitrogen has got seven electrons. Two of the electrons are situated in the inner shell, and the remainder, which are the 5 electrons, in the outer shell. That can be stated like that: 5. NH3 formed 3 covalent bonds with the hydrogens, and then the remainder is a pair of electrons which is unshared. It has got what? Unshared pair of electrons. A proton, the orbital of a proton has nothing, no electron. So whenever a proton has tendency to react with the ammonia to form, the result will be NH4 positive. What will happen? The proton is going to react or form bond with the ammonia by what? By accepting a pair of electron, and then ammonia donates that pair of electron. Ammonia donates a pair of electron to H. H here accepts a pair of electron. Anything according to the Lewis's definition which accepts a pair of electron to form a covalent bond will be what? A Lewis's acid. So here H positive is what? Is Lewis acid, and ammonia, we'll be talking later, is a Lewis base which donates a pair of electron. The tips to recognize the Lewis acids, guys. We have several tips to recognize the Lewis acids. We'll be talking about them in detail. Usually, for most of the cations in the reactant, they are classified as Lewis acids. The cation in the reactant are what? All positive ions in the reactant are what? Are Lewis acids. Like what? Ag positive with ammonia, aluminum positive 3 with H2O, proton with the ammonia. So all of these positives are what? Are Lewis acids. First. Second, elements with empty orbitals like boron and aluminum are what? Are also the Lewis acids. The definition of Lewis can be applied for any chemicals regardless to the medium of the reaction, guys. Here, for example, BF3 is in the gaseous, reacts with the ammonia. So BF3 accepts a pair of electron. It be a Lewis acid. That's why we have no restriction. This is an example to say we have no restriction of what? No restriction of medium for the Lewis, for a species to be a Lewis acid or a Lewis base. Any compound which the central atom has 3 valence electron and form a 3 covalent bond can be a Lewis acid. Like what? In our book we have got 2 examples, BF3 and AlCl3. Guys, when the BF3, the above, here we have the BF3, reacts with the ammonia. This is a central atom, B is a central atom, formed 3 covalent bond with F. So the general form of this compound, this central atom, is what? AB3. We can say it's AB3. The A is a central atom and the B are the atoms they are surrounding the central. Such type of molecules, they become what? They become Lewis acids. Why? Because they have empty orbitals to accept pair of electrons. But we have to be careful that the ammonia, which is NH3, is in the same form, but it's not the Lewis acid, instead it's Lewis base. That's why you have to take an exceptional, except the ammonia. We have got BF3 plus F negative, which is what? Which here the F negative has got valence electrons, donates a pair of the electrons to the BF3 and then to form BF4 negative. That's why BF3 is the Lewis acid and F negative is the Lewis base. We have a note, guys, here for the donation of the protons. Any molecule ion which donate a proton is not classified as Lewis acid. So guys, any molecule or ion that donate a proton cannot be classified as Lewis acid. Only Bronsted-Lowry acid, so it can be only Bronsted-Lowry acid. So all binary acids and oxyacids are not defined by Lewis's definition. The binary acids and the oxyacids which they donate protons, in the opposite, they will not accept pair of electrons. If they do not accept a pair of electrons, they cannot be classified as the Lewis acid. So you have to know this note, which the binary and the oxyacids are not classified as Lewis acids. Lewis base, guys. We talked about the Lewis acid. We said Lewis acid accepts a pair of electrons. So that pair of electrons comes from what? From a Lewis base, which donates a pair of electrons. So a Lewis base is an atom, ion, or molecule which donates a pair of electrons to form a covalent bond. So the two keywords are important: donates a pair of electrons to form a covalent bond. The tips to recognize the Lewis bases: all the anions, guys, all the anions in the reactant are what? Are proton, electron donors. Those that the electron donors, they can be classified as the Lewis base, but we have exceptional, except what? Except if they do not donate protons. So all negative ions are what? Are classified as Lewis base, except those that they donate protons. For example, here Cl negative, F negative, it's without protons. That's why it has no protons. It can be classified as Lewis bases. But have a look on the other example. Hs negative plus H2O will produce hydronium plus S2 negatives. In this case, guys, HS negative is donating a proton. So when it donates a proton, it cannot be a Lewis acid. It's only Bronsted-Lowry acid. That's the note we have to know. H2O and ammonia, they can be proton donors. So according to Lewis, H2O is what? H2O is Lewis base only. But when they donate protons, they cannot be Lewis definition. They cannot deal as the Lewis's definition. And we have got an example, a note here. Any molecule ion which accept a proton, must donate a pair of electrons to that proton. So all Bronsted bases are Lewis bases too, but all Lewis bases are not Bronsted-Lowry bases as well. Let me provide an example, guys. When something, for example here, H2O accepts a proton. When it accepts a proton, it's a Bronsted-Lowry base. And when it accepts a proton, it must donate a pair of electrons to that, so it becomes a Lewis base too. But we have some examples that, so we can say all Bronsted-Lowry bases are Lewis bases. But all the Lewis bases are not Bronsted-Lowry bases. So how? Example here, F negative is Lewis base, but it's not a Bronsted-Lowry base. That's the statement which we said. So ammonia and H2O, as I said, are the Bronsted-Lowry bases, but if they do not donate the proton. If they donate proton, they cannot be classified as Bronsted-Lowry bases. They cannot be classified as Lewis bases. Sorry, guys. Lewis acid-base definitions are what is the formation of one or more covalent bonds between an electron pair donor and an electron pair acceptor. Usually, the structure of the Lewis reaction follows as that acid plus base to form AB, a compound. So, two reactants and one